This is going to be review video 24, Arrhenius acids and bases. So let's start out by defining what that even means. The Arrhenius acid and base definition is one of two definitions that we'll look at, the other being Bronsted-Lowry. But basically, you can have acidic or basic character in a lot of different ways, and the Arrhenius definition is just one of those ways. So, an Arrhenius acid is basically a substance that produces either H plus or H3O plus ions in water, and an Arrhenius base is a substance that produces hydroxide ions in water. And so in this little doodle down here, I've kind of showed you how that works. So on the left-hand side with Arrhenius acids, we have a water molecule and the acid, hydrochloric acid, interacting with one another. And what happens during that interaction is essentially there's an attraction between the oxygen of water and the hydrogen in the hydrochloric acid, and that attraction is in fact strong enough to break the bond between H and Cl. And instead of just floating off into space and being an H plus by itself, that hydrogen is actually going to attach itself to water, turning the water into H3O plus, which is hydronium. And then you have a chlorine ion just kind of floating off by itself in the case of hydrochloric acid. And that's why I said up here that substance produces either H plus or H3O plus, because you can kind of think of both of those things as the same entity, since the H that's breaking off here is an H plus for a second, and then once it attaches over here to the water, it creates an H3O plus molecule. All right. If we're talking about an Arrhenius base, we can see our water molecule and our base sodium hydroxide interacting with one another. What's happening here is there's an attraction between the oxygen on water and the sodium that's attached to that oxygen. And that sodium is going to break off and associate with water over here. It's not going to attach to the oxygen. It's just going to float around next to it because this is a dissolved ion at that point, and it's going to leave behind a hydroxide ion, or OH minus. Basically, if you're looking at a formula and you're like, is this an Arrhenius acid? Is it an Arrhenius base? If you're looking at a formula and it has a hydrogen listed first in the formula, that's probably an Arrhenius acid. So HNO3 is nitric acid, HCl is hydrochloric acid, H2SO4 is sulfuric acid. If you're looking at a formula and you see a hydroxide or an OH listed at the end of the formula, like in sodium hydroxide, magnesium hydroxide, and iron 3 hydroxide, that is probably an Arrhenius base. In terms of acids and bases, we can split them up beyond just calling them an acid or a base. We can call them either a strong acid or a base, or we can call them a weak acid or a base. And so the difference there is just the degree to which those things break up in water. Because again, up here, when we were talking about that, our acid HCl broke up into two pieces. Our sodium hydroxide broke up into two pieces. And so the degree to which they can do that defines their strength. All right? So a strong acid or a base is going to break up or dissociate completely. The reason that that makes it strong is because when you get a lot of dissociation, you get a lot of H plus or OH minus ions. And these two ions, once they interact with the things around them, are what are giving those substances acidic or basic character. So if you get a lot of H plus, a lot of H3O plus, or you get a lot of OH minus ions, then you have a strong or a powerful acid and base. Weak ones, however, do not dissociate or break up completely in water. So instead of breaking up into like H plus and Cl minus, if HCl were a weak acid, only a few of those H pluses would break off and most of that acid would remain together as an HCl molecule. But little dissociation results in few of these in your solution, which means it's a less powerful acid or a less powerful base. These two tables tell you the list of strong acids and strong bases that we have to worry about. So all the ones over here, hydrochloric, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric acid, those are the strong acids that you need to worry about. There are a couple more that can be defined as strong or strong adjacent, but these are the ones you need to be concerned about. Over here in the strong bases table, we have a few more. We have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, cesium, calcium, strontium, and barium hydroxide, which seems like a lot more than the acids. But again, that's really just a few of the bases that exist. Down here on the bottom end of the table are a couple of common weak acids and a couple of common weak bases that I want you to be aware of. Acetic acid or vinegar is a very common weak acid that the AP test will use a lot, and you can see that formula a couple of different ways. You could see it either written as HC2H3O2 or CH3COOH. Those are the same formula written differently. And then another common weak acid is hydrofluoric acid or HF. Couple of common weak bases, we've got ammonia, which doesn't actually have a hydroxide in it, but it is still basic for reasons that I'll go over later. And then sodium bicarbonate or baking soda, NaHCO3. The bad news for you is that you do in fact have to memorize these, but the good news is that there's an easy way to do that, because chlorine, bromine, and iodine, those are all halogens. And then nitrate, sulfate, and perchlorate, those are all 8 polyatomics. So if you remember halogens and 8, you're most of the way there. The only exception to the halogens rule is going to be HF, and we'll go over why that's an exception to it second semester. In terms of memorizing your strong bases, lithium, sodium, potassium, rubidium, and cesium are all group 1 metals. Calcium, strontium, barium are all group 2 metals. So if you remember group 1 and then a few of group 2, then again, you're halfway to memorizing your strong bases. If you have an issue memorizing or understanding any of this, please let me know.